break my heart in the morning. Wait till later.
Okay. I get great pleasure of torturing students, that's why. All righty. Well, I was chit-chatting there with Don, and time got away from me, so we are a little late. I'll get us started right away. I'll start with the little package, if you will, of the first ones you turned in. A little slow getting those back to you, but then again, I guess that's...
as long as they're all before the exam is fine.
Yeah.
They're still working.
Yeah. Don wanted me to tell you to make sure that the solutions are posted and that he's got a review scheduling coming up for you on Tuesday. And of course, you have the MC tomorrow. And so we're 1 week away from our test. And it is chapters from the beginning, 23, 24, 25, and now into 26. So we did a little bit on 26, not too much, obviously, but let's continue. Yeah.
Just one thing. You know you always have those review questions?
Yeah.
Can we get them earlier?
Most likely you can, because I've seen Don do that, but ask Don.
Okay.
Yeah. So it's, and I saw him putting it together, so I think so. All right, well, as you hopefully recall from Tuesday, and maybe we'll start again here with this little show and tell device here, but we were learning about capacitors. And I took the hour, a little less than an hour here, to really try to get across here what is a capacitor and what is the capacitance of a capacitor. And so we did kind of the simplest one before we left, which was just a parallel plate. In fact, maybe I should put that way over here. When we left, we had a parallel plate. And so I brought my parallel plate out here again to kind of just physically illustrate. This is the idea of a capacitor. You've got two metal plates, and if you move charges, so a bunch of electrons, from one plate over to the other, one will be positive, one will be negative. The amount of positive will be equal to the amount of negative, so the total charge on the capacitor is zero. But that is the idea of a capacitor. It stores charge. And you saw me at least show you one reason why we care about capacitors. Like I said, we'll see at least 3 or 4 before the semester's over, but this was our first one.
You said move. Can you just create a dipole and not move any electrons?
I don't know if you want to... I'm not completely opposed with the word dipole either, but I like the word move, because I literally will take some negatives off of here and put them onto there. Now, if you think of it as one big unit, you might just call that a dipole instead, because they didn't leave the whole unit. But they did leave one plate and go to the other one. A lot like a water molecule, you'll say it's polarized. No electrons actually leave the molecule, but the electron does leave the hydrogen atom and move over to the oxygen atom. And so I'm saying the same here. And so I have, and maybe I should backtrack even further here, a picture that might look something like this, where I've got a plate, 2 parallel plates, and on one plate I have a positive charge, on the other plate I have some negative charges, and those charges are stored there. And so the whole semester, the whole chapter, including the lab we did this week, or for a third of you, the lab you will do this afternoon, the whole idea is to get you familiar with capacitors and some other interesting things about capacitors that we didn't get a chance to talk to on Tuesday. Some of you already saw because you did the lab. Actually, 2/3 of you already saw the lab, and then we'll jump into some example of this. But we left this idea that the capacitance then, at least for the parallel plate capacitor, was calculated this way. And we figured out the electric field from the parallel plate. From there we integrated it, and we got the capacitance. That's worth doing again, just to see the fundamental basics of a capacitor. So I thought I'd start this morning by saying, all right, let's do it again. Let's do the capacitance for these coaxial cables. Last time I passed a couple of them around. I'll do it again, just so that make sure that everybody gets a chance to see these. We're going to use coaxial cables again and again and again and again. And so I'll pass them around. They've been stripped away so that you will hopefully see that there is an inner conductor, and then around it is an outer conductor. You might even give some thickness to the outer conductor if you like. But the point is, we would have two pieces of metal, and if we move charges from one to the other, so usually we make the center one positive and the outer one negative, but we would then store some charge. And that could be a good thing or a bad thing, as I'll mention a bad thing about it in just a second, because I think you last time saw the good thing about having a capacitance. The good thing about having the capacitance, and this one in particular we used last time, is I can charge it up and then I can use that to run that light bulb. And you saw that for a few minutes. In fact, that was step 9 of the lab. The last step you did, you were asked to, hey, take that same capacitor, charge it up, or you guys this afternoon, that's what you will be asked to do. Kind of look at it yourself here. So there should be a nice little formula. So keeping this one in mind, this is the one for a parallel plate capacitor. Let's ask this question, and what would be the capacitance for a coaxial cable? All right, well, let me give some dimensions on here. Let's say the cable itself is length L. Let's say then the radius of that inner conductor is R. Did we use A last time? Wanted to be consistent. I can't remember. RA for the inner one? RB?
Yeah, the outer one.
Okay, so I'll use B. And the outer one I used A? Okay. So we'll use an RA for the outer one, although now that I'm trying to be consistent, I just realized I think your book might actually do the opposite, so it doesn't help me to be, yeah. So, but hopefully you'll make that connection. There's an inner radius and an outer radius, and I should be careful too. The outer radius right here really probably needs to be said better. It is the inner radius of the outer conductor, right? Because the outer conductor also has some thickness to it. But hopefully you get the physical picture that what I'm saying here is there would then be an electric field that would be radially outward. Okay? The centerpiece could have either charge, but I'm going to label it as a positive. The inner wall of the outer piece would then be negative, and that's why the electric field then would go from the outer radius of the inner conductor to the inner radius of the outer conductor. And what I was trying to show here in the beginning part here is the capacitance is defined this way. How much charge is on one of the plates, either positive or negative, doesn't really matter, when you apply 1 volt to it, when you charge it up to 1 volt. And so again, I think one of the tricky things about capacitance is, unlike saying I have a 5-gallon bucket, a 5-gallon bucket means you can put up to 5 gallons. You could have less than 5, but you can't have more than 5 because the water doesn't fit. Capacitors aren't quite labeled that way. So you'll hear me say again and again, oh, think of this capacitor as a bucket of water. And you'll hear that analogy later on here today. But I want to be a little careful. It's not quite the same thing. This is how much do you get for every voltage of charge. So, as we saw last time, this one, which by the way has a very large rating of 1 farad, this 1 farad capacitor means that it has 1 coulomb of charge if we charge it up to 5 volts. I mean 1 volt, sorry. But we did charge it to 5 volts, which means how much charge was on? 5 coulombs, right? And so I would have to take the voltage, 5, multiply it by the capacitance, 1, and get 5 coulombs. So we charged this to 5 coulombs. And you did too in the lab, or you will today into the lab. So, as we did for the parallel plate, let's take a close look at how you're going to calculate this. How are you going to get the voltage from the 2 conducting surfaces? Well, like we did here, in order to get that, we have to integrate the electric field. And so this voltage, the change in voltage, is minus the integral of E dot dr. Well, that means, of course, in order to get the voltage, which I should point out, this is chapter 26, this is chapter 25, and now we're going to go back here to chapter 24, Gauss's law. How do I get the electric field? Well, we did this one actually recently, I think it was Tuesday. We kind of backtracked and said, let's look at the electric field. We'll do a Gaussian surface. Oh yeah, we had that example with the Geiger counter, and we wanted to know the electric field in there. And so I will then apply Gauss's law first to get the electric field. From there, I will integrate the electric field to get the voltage, and from there I will finally get into chapter 26 and get the capacitance. So going all the way back a couple of chapters here, let's find that electric field again. So I have made a cylindrical shape, kind of in the green here, my Gaussian surface. And if you kind of wrap this thing all the way around, here's my, surface kind of wrapping around. As we've argued, I'll do it a little quicker again, is that the electric field would be radially outward. So the angle between the electric field and the surface would be 0 along this rounded part. Along the top and bottom of the cylinder, the angle would be 90 degrees. And cosine of 90 degrees is 0. And so when I do an integral over a closed surface, I would have an integral on the top piece plus an integral on the bottom piece plus an integral on the face. And my argument is top and the bottom making up the closed face give me 0 because of the angle. The face part of it then reduces to that much in the first step. The second part then says you can factor out the electric field because by symmetry we argued that the electric field would be the same value everywhere on the Gaussian surface. Don't miss that. I emphasize that in 24. I'm not saying the electric field is a constant everywhere inside my coaxial cable, but I'm saying it is a constant everywhere on my Gaussian surface. So I pull it out of the integral related to my Gaussian surface. And then what I get then is a equation that labels the electric field, which is what I'd like to solve for, and then this would be the area of this wraparound face. And I may or may not make the Gaussian surface as long as the coaxial cable, but it would be some length L, whether you want to call those the same L or not. Maybe it's easier just to call them the same L. It shouldn't show up in my final equation, as I mentioned. I don't expect the electric field to depend upon the shape or the size of my Gaussian surface. That's just an artificial part of doing the calculation of the physical world. The other side of the equation, of course, is the charge inside over epsilon naught. And the charge inside is only the charge on the inner conductor. And so if we say the inner conductor has a charge per length of lambda, then that would be the charge inside. And the L does cancel off as to be expected. And we get the same electric field we got last Tuesday, we got back in chapter 24. It says this, that the electric field is 1 over 2 pi epsilon naught lambda over r. And so we have an electric field that depends upon where you are radially outward. That's why when we did a Gaussian surface that had the symmetry of a constant R value, a cylinder, the electric field is a constant along that, but if we move further out or closer in, the electric field would change. So this tells me something that hopefully we already remember from last chapter, that the electric field is very strong here near the surface and gets weaker and weaker and weaker and weaker, although it still could be pretty strong if this is a small object, as those coaxial cables I passed around. So now, knowing this electric field, I can then get the voltage difference. And again, we did that on Tuesday, not really starting this chapter yet, but that was our last example with the Geiger counter to get the voltage between those two surfaces. We didn't take it one step more to get to here, so I will in a second. But let me now get the equation for the voltage difference between my two surfaces. So I am going to integrate from R sub B to R sub A. And so now that I know the equation for the electric field, it starts here on the surface of the conductor, moves radially outward until I get to the inner surface of the outer conductor. So this is 1 over 2 pi epsilon naught lambda over R. And I'll be moving outward, straight radially outward. That's nice, because then I can just call my direction dr, and the angle then is 0 degrees. The electric field is radially outward, and the direction that I am going to do my integral, which those of you further in math, you would call this a line integral, right? I'm going to add up along a line. This happens to be the electric field line. Yeah.
Sometimes you would use charge over length or and charge over area or charge over volume. When do you know what is appropriate for this problem?
Oh, yeah, it's not so easy to know if I'm going to use charge per area, charge per length, charge per volume. I suppose you might argue that it's always charge per volume. But really the answer comes down to the symmetry here. And in this case, I am only looking then at the charge inside, okay? And the inside is the length of the cable. So I want charge per length, because I'm going to multiply by length. If I had a big surface inside there, which you might argue that I technically do, right? I would then use a area here, and so then I would use my sigma. I would have charge per length.
That one has a volume also.
Yeah, but it's a conductor, so where is the charge? Yeah, it's on the surface. So you could have, if you wanted to view it slightly different, say it's a sigma, it's a charge per area, and then figure out what the area is of this surface area of the inner conductor along here. And then so I would write that as 2 pi r sub b for the circumference times length L. And all I'm saying is that really is then charge per length, right? Okay. So that's a long way of saying there is no right or wrong way. There is how you're going to break it down into its pieces. And I would suggest breaking it down into the lowest dimension. So if you can do charge per length, and that's what I suppose more physically this would make a whole lot more sense, because you know the charge is distributed over. Oh, fair. There should be a negative, but I'll come back to here. I'm really interested when I do capacitance, not worried about the direction of the sign. So we're just dealing with absolute numbers. So instead of me putting a negative there, how about if I just do that? All right. And so I'll just, drop the negative all together. And all right, so continuing on here, I can do this integral. And fortunately, it's not a hard integral to do. I get a lambda that I can pull out in front. I get the 2 pi epsilon naught. I can pull it out in front. And then I get the integral of 1 over r dr, which becomes the natural log of r, evaluated from rb to ra. And so my delta V, at least the magnitude, would be then a lambda over 2 pi epsilon naught ln, and then I would have an RA over an RB. I think your author, when we got this for the Geiger counter, did one more step, and I will too, because I'm gonna put it right in here. Is I'm gonna look a little closely at it, starting with the idea of maybe I should replace the charge per length, lambda, with what it really implies, the whole charge on that inner conductor divided by the whole length of my coaxial cable. So I will replace lambda here. This one's worth discussing because when is a logarithm greater than 1, or excuse me, greater than 0 and less than 0? When is this number positive or negative? Because remember, I want to find the absolute value. Yeah, and anytime you take a log greater than 1, you get positive. Anytime you take a log less than 1, you get a negative. So the way I have it written, I just wanted to check if it's the correct ratio. In other words, which is the smaller one? It's RB, right? Did I? Yeah, from B to A. Okay, good. Good. So that is already a positive number. I was thinking it might come out to be a negative number. But had it come out to be a negative number, feel free to flip it over, because that's just the negative, right? And we're just looking at absolute values anyway. So in this case, I already have a positive value, so there's no change I really need to make. I'll just kind of remember then that the smaller one is down here and the bigger one is up there. Okay? That's the voltage. Finally then, I can actually get to chapter 26. And you might be happy to see it's the easiest part. The harder part is the old stuff, the stuff that hopefully is already sinking in. How do you get the electric field from Gauss's law? How do you get the voltage from chapter 25 here? You integrate the electric field. Or you add up the potential from a bunch of point charges. That works too. And you saw me do a bunch of those examples. But this one was easy, just to integrate the electric field. So with that said, I can finally finish this and say, okay, what is then the capacitance for this coaxial cable? And so I will put the charge in there and then divide it by the voltage here. And so the voltage is charge over 2 pi epsilon naught L natural log of RA over RB. And so the Q's cancel off. The denominator of the denominator flips over, and then I have an ln of RA and RB. And so there's the equation for my capacitance of this capacitor. Now let's point something out. Notice the capacitance depends on geometric factors, right? How long is my cable? What is the ratio of the radii? Now, didn't we see that for the parallel plate? The parallel plate, what did the capacitance depend on? Yeah, the area and the distance between them, a bunch of geometric factors. What you will notice, whether we have parallel plates or a coaxial cable or spheres wrapped around spheres, or what we were talking about earlier, you take two sheets, you roll them up and you get more of a spiral, it'll always depend upon the geometric factors. And so it's how you build it. How much surface area you have, how much distance is between them. There is some connection to the geometric properties, and that's the whole design of the capacitor. And so you see, in this case, of course, the capacitance would change with how long it is. I think your author writes it this way. He says, let's label this in a more useful form, in the sense that we can say, how much capacitance do you get for every meter? Because you may have a short cable like 1 meter, or if this cable is running across the telephone lines, going across the city, this could be thousands and thousands of feet of cable before it goes from Time Warner station over to your house. And so I think the cable in my house is like 18,000 feet. I'll mention why that's relevant. That's a long way, but it ends up with a lot of capacitance. Annoying a lot of capacitance, I might add. Because this would mean, well, this is the formula that your author lists. But this is saying then that if you want a lot of capacitance, well, either make this ratio a big number or make the cable really long. And 18,000 feet over to my house means that there's a lot of capacitance on that cable. Now, that's great if I wanted to store up a charge and run a light bulb on it. I would like a lot of capacitance. But if I am trying to surf the web, it's not such a good thing. Why?
It's not constant. It keeps going down.
Well, let's come back to here. The voltage, if I write it a different way, would be charge divided by the capacitance, right? Okay, so if I need to send data down this coaxial cable, which is often what we like to do, then what we have to do is charge up that cable, right? We've got to put a certain amount of charge on there. And we've got to put enough charge until the voltage goes to 5 volts. So if you know a little bit about technology, this is the idea of those coaxial cables. That voltage goes up and up and up until 5. And then it goes and resets and 5 again and 5 again. And the pattern of which it goes up to 5 and down, what we call the on-off, the charging and discharging of that cable, that is the information. And so as I try to surf the web and read my emails or watch a YouTube video, as that information comes, that cable has to charge and discharge, charge and discharge, charge and discharge. Now, if I have a lot of capacitance in that cable, what does it say about the charge? I got to get a lot of charge in order to bring it up to 5 volts. Now that may take a little while. So somebody like myself who's 18,000 feet away, it's going to take a while for that cable to build up to 5 volts. What if somebody who lives close and the distance is maybe only a couple hundred feet of cable?
Is that what they call it? The ping time or latency?
Yeah. And this is how long it's going to take, or it's going to take me a lot longer for my cable to charge up compared to somebody who's a little bit closer. And the consequences of that is the information can't come to my house nearly as fast as it could to somebody else's house. And so you will notice that the speed of your internet can vary dramatically for a lot of reasons, not just this reason, but here is one reason. And so long cables have that unfortunate consequences. They have a lot of capacitance. So it's good that we have a coaxial cable, and it's bad that we have a coaxial cable. Yeah.
Is there a way, do like the cable companies or internet service providers, do they have like ways to recharge or?
Well, okay, yeah, so right, so halfway through what they could do is put what you might call a repeater. Right? You could say, all right, so instead of having this all charge up, what we'll do is we'll take a short mount and we'll do that, and then we will repeat it. Okay? Now, you're still waiting for that first one to charge up only to let that second one charge up. So that may or may not be a help. But yeah, you could do it. It's just now expensive. Right? And so they do have their standards where they say, okay, we are going to, and they're getting shorter and shorter. The old DSL line was a big challenge is because they would like, okay, we can't send that fast of information, and so people who were far away were always complaining about their speed. Still are, although the coaxial cables have kind of made up for it. But you guys are way too young to remember where cutting technology was 14 kilobytes a second. Oh. And I remember when they came out with a 28 modem. Whoa, double my speed. I got a 14K modem and now 28. Ooh. And then I think DSL came out, no, like 56? Is that? Like, oh wow, from 28 to 56. Oh, that is so fast. And now 56. I mean, you couldn't even watch a video at that rate. Yeah.
When I use fiber optic cable, it goes much faster.
Oh yeah, so yeah, I mean, if you really wanted to ramp up the speed, go to a fiber optic. But now you're talking expense, and you got to keep adding technology here. And so most of your phone companies have at least their main network where all the information. You guys are recipients of that here. We have a fiber optic that runs from here to UCSB. And the information can go very, very quickly through our campus network and over to UCSB. And of course, once it ties into UCSB, it gets the main AT&T. And I don't know if you've ever, gone to the beach anywhere out in Gaviota, but that whole Gaviota coast, you got to park somewhere and cross the railroad tracks. Look carefully when you cross the railroad tracks, because that whole 101 corridor there, that is the main utility hub up and down the whole coast. And so as you cross those tracks, you'll see signs that say, fiber cable, do not dig. You dig there, you have just cut Northern California from Southern California across. You have cut Southern California off from the whole Asian continent, because that fiber optic runs across to Hawaii, from Hawaii right into Morro Bay, down Morro Bay, and into eventually Los Angeles and the big network. But everything that goes overseas goes up that line. Don't break it.
That one main line cable, the backup cable?
Well, it's like this big around, and each fiber is like this, and each fiber handles 10 plus gigabytes a second. So there's a lot of stuff in there. There's other things too. There's other ones that say pipeline, do not break. And so if you break it there, you either break a natural gas pipeline or an oil pipeline from all the oil that's shipped around. You might even be surprised. It's that big oil line. Those oil rigs out there in the ocean, I mean, they've got, whoops, sorry about that. Forgot to turn off my phone. All right. But those rigs out there, they have all underground pipes, and those oil come in there and they go along. And most of that oil actually ends up in Texas before it refines it. So they've got a long way to go before it refines it, and then they'll refine it and use it.
It may be kind of silly, but do they actually run fiber optic cables through the ocean?
Under the ocean? Yeah. Yes. So there is a huge fiber optic that runs all the way up here into Morro Bay. There's a big, if you get to Morro Bay, there's a huge AT&T building there. All the data is running through there. That's why, if you're into latest news and political stories, the U.S. government owns the floor below AT&T. And all the data that goes to the top floor now gets siphoned off to the bottom floor, so that they can read and hear and everything. And I have no problem with it. It keeps us safe. So, but other people say, "Oh, I don't want anyone to read my email." Okay. My wife sent me an email, asked me to stop and get bread and milk on the way home. If that keeps me from being bombed, I'm good. You can read my email all you want. Whatever. And actually, I guess I should put a disclaimer. I don't think anybody's actually reading your email. They're keeping track of who you communicate with. Yeah. So that if someday they just suspect you of communicating, they can trace you all the way back for years and get the whole network.
And most of the time it's actually just code words that goes through a program and just picks.
Yeah, nobody can sit there and read all your email. They got to have a computer to scan it all. But Brazil's not happy with us. Germany's not happy with us. Prague's not happy with us. But all right. Anyways, I didn't mean to go down that road quite, but I wanted to show this one, and maybe that took a little bit longer than I had hoped. Let's keep going, because as you saw, one good main purpose of working with capacitors is in that they store energy. They store charges, and these charges then are what runs this light bulb. So let's do a quick calculation here. Let's ask ourselves, now that we have some capacitance, what is the energy stored in a capacitor. How much is here? Now, it probably doesn't surprise you that it does depend on the voltage. How much are you going to charge it up? It depends how big this thing is. And when I say big, I mean how much capacitance it has, because the capacitance doesn't necessarily represent, it has to be a big object. Obviously, it usually is, because more surface area means they're usually bigger, but we could roll it up real tight. In fact, we can get a lot of capacitance if we just get it real close. And so if we're able to get it real close and roll it up real tight, like this one, then we can actually get a lot of capacitance, even though the object itself is not very big. And so I'll be careful when I say big. I don't mean big in physical size, but I mean big in terms of its capacitance. But if you were to maybe draw a picture of a plate and say, all right, let me take a parallel plate, and imagine that you have already partially charged it, if you will. So you've got, some positive and some negative, and you want to keep charging it up. Well, all right. So I'm going to take another negative that is on here and move it over to there. So I'm going to move a charge of dq. All right, so how much energy would it take to move just a little bit of charge dq? Well, a little bit of energy then is going to be the little bit of charge that I have moved across, and so it depends on what voltage it is. And of course, what voltage it is depends how much you've already tried to move across. So it kind of makes sense that this is probably not going to be a linear function. In other words, the first chunk of charge is not going to take much energy. But by the time you've moved a lot of charge, now to move that same amount of chunk of charge over there is going to be really hard. And so you kind of expect that the buildup of energy starts kind of slow and gets more and more and more as you bring the charges over. And sure enough, that's what I want to say. I want to say, add this all up. Start with a charge of 0 and keep adding it up until you get a charge of capital Q. And so my question is, if I charge a capacitor to capital Q, how much energy is there?
Does it look familiar? It looks like you've seen this in the home before. Like, that
Yes.
thing
Yes. Good. Hopefully it all does look familiar, because this chapter and the next two chapters, with some exceptions, is we're not really studying so much of the physics, but we're saying applied physics. How can I use this? What was the whole point of getting electric fields, electric forces, electric potential? How could I use this? This is a good example. I can build a capacitor, and so this is our first one. And so there's energy stored there, and as we talked about, I can use that energy to run a light bulb. So I am going to do my integral dq. Now here's the neat thing about it. I will replace the voltage with, and I used to have it right here, so I will put it back, but I will remind you of the definition of the capacitance. It is charge per volt. So this integral could be changed to charge, and I'm going to put a little, bummer, I'm going to put a Q over a C. Saying if you have a capacitor, there'll be a certain voltage. Its voltage will depend on how much charge you have. Now I'm going to change it to a little q at this point, because this kind of our definition is what happens at the end when you have a total charge q. So partway through, while you are charging it up, I'm going to label that as a little q. And so at first, you would have no charge on the capacitor and therefore no voltage. But then you'd have a little bit of charge and you'd get a little bit of voltage. And then more charge and then more voltage. More charge and more voltage. So the voltage at any moment would be some kind of an equation that keeps changing as you are moving charges over. And so I don't want to put whole charge divided by C, because that's going to be the voltage when you're all said and done. But the beginning part's not going to take much energy. The beginning part, there's very little voltage there because there's very little charge. But fortunately, that's an easy integral to do. I'll put my limits on here. But I can pull out the 1 over C. That's why I was trying to point out. Notice in the parallel plate capacitor, the capacitance is a constant number. It's based on the geometry of how these plates are built. How close are they? Are they wrapped around in a circle, in a cylinder? Are they parallel? And so each of these equations for capacitance, really in terms of using a capacitor, once it's built, the capacitance doesn't change. That's why all these capacitors that I pointed out in lab, and 2/3 of you have done them, the other third will see them today, but all these have a number. That is its capacitance. It's based on some geometric factors in there. How close are the plates? How big are the plates? How tightly are they wrapped together? And it doesn't matter if I charge it up to 1 volt, 2 volts, 10 volts, 20 volts, the capacitance is the same. Which then makes this integral real simple, because I just have a dq times a q, which, what the heck was I doing here? Oh, where'd that come from? Did I? Was I starting over there and okay, all right, now let me get rid of that. All right, so this then would become just a simply Q dq evaluated from 0 to capital Q. Fortunately, that's an easy one to do. It just becomes 2 squared over 2c. So there it is. The answer I'm looking for is what is the energy stored in the capacitor? And I hope it fits my intuition that I said earlier. Wouldn't I expect the energy to be a non-linear function? Right? I kind of would expect that if you just put a little bit of charge on there, it wouldn't be much energy. And so if I plotted how much energy is on this capacitor versus charge, it is quadratic in nature. And most of your energy then is near the end of the cycle, if you will. That's when it starts to get hard to put more charges on there. So we want to get, if we want energy, we want to get more and more and more charges on.
That also looks for the roll down.
Oh yeah, now notice, here's the neat thing about it. Notice that at this step for capacitance, I did not even specify what kind of capacitor I had. This could have been a parallel plate. This could have been a coaxial. This could have been some other shapes that we didn't work out here in class, but your author works out, or ones that you are asked to work out on the homework. All you need to know is its capacitance. So as we start to use these capacitors, you will notice something. That we would just say, here's the capacitance. And when you have something like this, and it says the capacitance is 1 microfarad, you don't really know how it's made. You don't know if it's rolled up. It probably is, just looking at the shape of it. But it could have been a bunch of discs. And so this could really be parallel plates. Probably not, that's expensive to make, but it could have been. And it wouldn't matter. All I need to know is the capacitance. And the capacitance is part of the geometry. So once we have the capacitance, we can go forward and not worry about how it is geometrically built. And so the physics part is, okay, it does depend upon geometry. Those of you will notice, I was going to say those of you in circuits, but I don't think you've done capacitors in circuits yet. Right? But you soon will. And whether it be in circuits or whether it be here, don't be surprised then if, as we start to use these in a practical application, we never specify, is this a parallel plate capacitor, or is this a coaxial one, or is this something else? We don't need to. So yes, this equation would be valid for any of our capacitors. We just need to know its capacitance. Now, I'll keep going with this, because although I put a box around it, and I think it makes good learning, it's probably not the best practical application, because it depends on how much charge you put on there. And to be quite honest, as you will see here in a second, when I go to charge some of these capacitors up, and I got a big one here, and maybe some smaller ones here, and we'll charge each of those up. But how will I charge them up? Well, I'll probably use one of these power supplies. And when I turn the power supply on, I will then turn the dial to get the voltage. So in this case, it's about 20 volts. Maybe I'll go down a little bit to 10 volts. But it might be a little bit nicer to talk about what is the energy on the capacitor based on the voltage. Because when I just hook this up, I know it's voltage. I'm not sure how much charge went on there. Of course, I could calculate that because they're mathematically connected. And let's put that together. I would remember this, that the capacitance is the charge divided by the voltage. So that means the charge times the voltage, the capacitance times the voltage is the charge on here. So when I take this power supply, if I do take it at 10 volts and I put it into here, I can then find, okay, what's the capacitance? Now this happens to say 10 microfarads. So I know that this is 10 microfarads. I multiply by 10 volts. I would get how much charge. I could then put the charge into here. And so if I put these two together, I will get something that I think is a little more useful in terms of actually doing our calculations. I will put a C squared and a D squared for the Q upstairs and put a 2C and get 1/2 CV squared. And to be quite honest, this is the one I commit to memory, not that one. Even though I think this one gives you a little bit more physical insight to what's going on. This is the one that is actually going to be practical. This is the one where you're going to take the capacitor, you're going to hook it to a power supply, and you're going to know its voltage. And so you're going to reach in here and say, hey, let's take a capacitor. Now this one happens to be 10 microfarads. So if I go to calculate how much energy is on this, I can put 10 microfarads for the capacitor. Then I can put in the voltage that I'm going to charge it up to. Now this one I had here at 10, and I could, but that would be much easier. So I got this power supply, which needs to be plugged in. But to illustrate some energy here, this bigger power supply goes up to 400 volts. Maybe a little careful here. This, as you will see in a minute, I will charge that capacitor to 400 volts. Obviously a lot more than 10 volts. And I guess as long as I'm careful, I won't get hurt here. But I wanted you to see a calculation for the energy. And I wanted you to see the energy stored there. This is enough energy that you can see and feel the effects of the energy. If I grab my calculator, let's see what that comes out to be mathematically. I have a half times 10 micro times 400 squared. And it comes out to be 0.8. 0.8 what? Okay, I hear some of you saying joules. Why are you saying joules? Okay, good. We're back to our unit analysis. We're saying energy. It should come out to be joules, right? So let's check it. Does that come out to be? What happens when I take a farad and I multiply by voltage squared? All right, so what was a farad? Coulombs per volt. And so when I multiply by volts squared, I get coulombs per volt. And I guess I should put these in parentheses, which is kind of our way of indicating, these aren't variables that I'm multiplying by, these are the units. Okay. What was the definition of a volt? Joule per coulomb, right? And so what are you left with? Joules. Okay, so not a big surprise, but it's neat to go back and see, especially since I think these units are new to many of you. It takes me all the way back to Physics 121 in Chapter 1, our unit analysis. What are you going to do when you have units you've never seen before? Same rules of mathematics for all of our units. And so we need to go back and remember the definitions, of course. But as we multiply and divide and cancel off, if our logic is correct, our unit should come out to be the appropriate unit for the measurement. And that's what we mean by a unit analysis. So this should give me a little bit less than 1 joule of energy. Not that much energy overall, but hopefully enough to see. And so let me be a little careful here, but I'm going to take and put the negative then to this plate here, and the positive then to this plate here. And you can imagine inside there's this column of parallel plates. And so then, and that's kind of a little safety switch where kind of sitting in standby and saying, okay, look, this is 400 volts. Do you really want 400 volts? So turn on a second switch. Yes, I do. And then the dial. And at least for those of you who are close enough, you can probably see this dial move. 400 is right on the end, and so I will go up and up and up and up, and right now it's at 100, a little over 100 volts, a little over 200 volts, a little past 300 volts, and not quite to 400 volts, but it looks like as high as the power supply is going to go. So I got about 380 volts there. And so what I have is I have some stored energy, that much energy. I could use that energy, right? I could demonstrate that there's energy here. And I will. What if I then unplugged it here, the positive, and I brought it and I touched the negative? Yeah, wouldn't the positives and negatives rush together, right? Wouldn't they be releasing all of this energy in the process? And you might be more familiar with this in terms of an arc welder. You build up the charge, and then when you touch the metal pieces together, there will be a huge flow as it goes from one to another. Let it discharge here a little bit. And one more time. Just because I can, right? And so if we kind of put them together, you'll see the release of energy as it goes from one to another. And so there's our energy and at least our calculation. Let's dive a little bit deeper into this capacitor. Let's ask this question. Now that I have this capacitor with stored energy, and I can now calculate its energy, I might begin to ask, where is this energy being stored? Or maybe, how is it being stored? I mean, what would you kind of describe where it is? Let's play with that equation for a moment. We have 1/2 CV squared, right? We have a parallel plate capacitor. Maybe it looks something like this. Let's put in the formula, at least for a parallel plate capacitor. Now, granted, my equation didn't only apply to a parallel plate capacitor, but it certainly did apply also to a parallel plate capacitor. So let me just put in the equation for the capacitance of a parallel plate. Let me also put in the equation for the voltage between a parallel plate. Now, maybe this one's worth reviewing here. This goes back to Tuesday, but when we did the voltage was the integral of E dot dr. We argued that the electric field would be a constant between a parallel plate. Not what we just did for a coaxial cable, but okay, so this is just for a parallel plate. Now, so is this. So I wouldn't call what I'm doing now a complete proof, but it I think illustrates the point I'm trying to get across. It's the easiest one to work with. That if you then say that the voltage between them is the electric field times distance, I can then say here is the electric field times the distance squared. Now, why is that helpful? Well, this would become electric field squared and distance squared. The distance down squared will cancel with 1 upstairs. And remember that D is the distance between the plate. In this picture here, we would be talking about D, distance between the plates, and A, remember, is the surface area of those plates. If I were to rewrite this, in this order, maybe then it might give a little bit of insight here. What is that? Volume, right? This is the volume between the two plates. This is the volume where there is an electric field. And so what I'm after here would kind of be the meaning of that. What would you call that crazy thing then? If this is energy here, yeah, this must be how much energy do you have per volume. And so we're going to refer to that as the energy density. And it's going to give us hopefully some physical insight to say, where is that energy? In the electric field. That energy density. What's in the equation for the energy density? The electric field. The electric field is really nature's way of saying, let's store this energy. And so the energy is not so much the charges themselves. The energy is actually the force needed to separate those charges. The energy then is in the field. And so we are going to call that its energy density. We're going to give it a symbol little u sub e. And little u sub e is this 1/2 epsilon naught e squared. This is how much energy do you get per volume. And so anywhere there is an electric field, what are we really saying then? That's a stored energy. And it's then if you have the electric field over a space, you can add up the energy densities throughout the space and get the total energy stored within it. And so this formula you'll see a little bit now and again as we get towards the end of this class where we have both electric and magnetic fields, and we're going to say, well, how much energy is there? We can come back here and go energy density. The electric field is storing our energy. All right, well, let's keep talking a little bit more about these capacitors. Now that we've done this whole idea that they have energy and you see that they have some energy, you probably notice that so far in my discussions here, I've kind of ignored what's in between. What if I were to put something in between? Would that make any effect?
Depends on if it's conducting.
And at least those of you who did the lab, hopefully you saw this yesterday in the lab. This was the point of step 8 in the lab. Let me start with this. Let me take this piece of vinyl out and make sure my plates aren't touching. And I'm going to hook a capacitance meter. And I'm a little concerned that it's touching right there. So you know what? I knew this would happen. So I brought our better ones, which those of you who did the lab will recognize it. These are the ones from lab, where we've got a nice polished surface here, and we've got 2 electrodes. It's just they're harder to keep separated. So what I'm going to do is put little tiny pieces of plastic there, but they're tiny. And the idea of being tiny, for those of you who haven't done the lab, is to say it's almost like the plastic isn't there. I mean, of course it is there and it's holding it up, but it's such a small percentage of the overall area that I'm just going to pretend that what I have then is a capacitor that is a parallel plate that has only air in between it, and that would be our calculation. Actually, I should emphasize that I probably am really treating it as nothing is in between it, not even air. Because when we analyzed this, remember we said, oh, there's free space. There's nothing in between, right? This is the permittivity of free space. Now, if I take a couple of wires and measure this, and take a black one and a yellow one here, and like those of you who done the lab, you did this. You hooked it up, and then you turned on our capacitance meter, and it wasn't much, so you put it on the lowest setting, but you got somewhere around 150 picofarads of capacitance, and sure enough, this one says 145. Okay? Now, of course, the capacitance, as we already talked about, should change if I change the distance and the area. I'm not going to bother to mention those. You already know that. In fact, that's also part of the lab. That was step 7, and those of you who are going to do a measurement here, you're going to change the distance between them. But in step 8, you were asked, that's a little too big a piece to tell where my circles are, but you were asked to take that same capacitor, which I just got about 145 picofarads, and then put some material in there. And what you were supposed to notice if you've done the lab, or what you will notice when you do the lab today, is this does have an effect. And so it's not just the distance and the area, that's a big piece of it, but also what is in between. In fact, if I hold this up now, it's off the scale. So I'm going to click over to the next setting, which, by the way, is in nanometers. So this says 0.497 nanometers. So this now becomes 0.497 nanofarads. I'll go ahead and call this the new capacitance. Or this is the capacitance now that the material is in there. If I write this in picofarads, this would move over 3 decimals. So this is 497 picofarads. So first thing I want you to notice, which is the whole point of you doing it in the lab, was to hook it up and notice, hey, the capacitance is bigger. I want to ask why. Why is the capacitance bigger? Yeah.
So that constant, the epsilon naught, is the permittivity of free space.
Free space.
So we're thinking without the material there, that would be, I mean, if it's not vacuum, but we would be thinking of it as free space. So would it be that?
You mean when the air was in here?
Right.
Right.
So this material would be a different permittivity?
Right. So this number, and now you can see the name a little bit better, right? It is how the electric field permeates free space. It'll be different if it's in air. It'll be different if it's the vinyl. It would be different if it's paper. And so in lab, you guys were asked to do this with vinyl and with paper. Now, before we go any further and introduce to, and here's what you're getting at, the dielectric constant, let me just give a picture. Here's what is hopefully happening. I have this parallel plate, and if I charge one side negative and the other side positive, there will be an electric field that is created between them. And the capacitance is defined as the charge per volt. And the voltage would be the size of the electric field times the distance. That was kind of this statement here, at least for a parallel plate. Here. Right? If you were to put some material in there, and so you don't have what we call free space, a vacuum. You actually have something there. They could be air molecules, which wouldn't change it by much because there's not that many. But you put a piece of vinyl there, or mica, or whatever. It will do the following. This material, and I won't fill the whole space for just a minute so I can do some drawings here. But the key for this to make sense is to realize that that material is made out of positive and negative charges also. And so all those pieces in there will then be pulled and tugged based on that electric field. And so what will happen, and maybe I'll draw it up here, although it's happening in here, is one molecule will then pull its electron, or maybe I should say push its electron to this side and leave the other side positive. Now remember, this is an insulator. So I'm not saying that the electron actually moves through the material. What I'm saying is it just moves on the molecule. It moves around the molecule. The molecule itself is polarized, not that it actually moves all the way across. But this is kind of what we did back in chapter 23, where if this was a conductor, we would have said the electron goes all the way to the other side, right? And so here's where the conducting material and the insulating material are a little different. Yet interesting, they come out to be a lot the same, because look at the next molecule. The next molecule would also be stretched according to this electric field, where negatives would go to the far side of the molecule. And in a sense, you might say the net effect of the positive and negative of those molecules on the inside cancel each other off. And although an electron did not actually move all the way to the second molecule, the first molecule is plus and the other one is minus. Look at the first molecule. The third molecule would again be a plus and a minus. It would be as if those two canceled off. And the net effect is what you would have saw with a conductor, right? With a conductor, you would have saw this side of the material positive and this side of the material negative. And so you might want to call it a dipole, sure. Now, it is still different than the conductor. And here's why. If this was a conductor, how many charges could move from one side to the other? All, as many as need to move in order to give you an electric field what inside? Zero. That's not going to happen for our insulator. So, our insulator, a couple of charges may stretch, but not all of them. And as a consequence of that, if we come back here to this electric field and maybe draw a couple more on here. 1, 2, 3, 4. I'll just do 5. With this material, the insulator, slightly... Oh, crap. I drew my electric field backwards, huh? You guys knew that. You were just testing me. Seeing when I noticed it, huh? Yes. Okay. Oh, I should do it in black. Okay, so. Now let me fix my electric field. Okay. So the electric field was going across here. And then I put that insulating material, and what's going to happen is the negatives, some of the negatives will stop some of the field. But not all of the fields. There's the difference. So, like I said, in a lot of sense, it's like a conductor. It's different in the sense that the electrons did not actually move all the way through the material. But as they stretch from molecule to molecule, it's equivalent to that. And so, just like we could say the metal was polarized before, we could say this is polarized. However, the metal would be completely polarized in the sense that there would be no electric field left inside of our metal. But for our insulator, there still is some electric field. It's weaker, right? But there still is. Now, let's come back to this equation. What if the electric field is now weaker? What does that say about the capacitance? It's a bigger number, right? And that's what we just saw in our measurement. We saw by me putting the vinyl in there, the vinyl becomes polarized. It reduces the electric field. A smaller electric field means more capacitance.
What happens if you put a conductor in?
Oh, now if I put a conductor, we can do the same logic, but now the field would be completely gone, right? If the conductor filled up the whole space, then there would be no capacitance anymore. If it had a little space front and back, as my picture kind of indicates, then what I would have is a short distance here and a short distance there.
You want the smallest electric field. Yeah.
Exactly. So here's this idea. The capacitance gets bigger and bigger and bigger as the electric field gets smaller and smaller and smaller. And so, oh yeah.
So bigger electric field is storing less energy.
No. Now, if you're going back to this equation, okay. Actually, we'll hold off. We'll play some tricky games here. But let's just understand the physics here for a moment, that this does reduce the electric field. We like to say this. We like to say that the new electric field has now been reduced by a factor. We use the Greek letter kappa. We call it its dielectric constant. And it has to do with the material. The field is weaker. This number right here is the dielectric constant. And so all of our capacitors that have really significant values aren't filled with air, as we kind of indicated on the first day. They put materials in there. The materials are a blessing and a curse. So far, we see the blessing, and if we want capacitance, that's a good thing. But it has some other negative consequences.
You said for charging your capacitor, the more you need to put more charge or more voltage through as you increase, like to get the electrons to go through. Like the last electrons need more charge, you said, or to get the electrons to move from one side to the other.
Yeah.
The last electrons need a lot more.
Oh, energy, right.
Energy. As far as the sign of the capacitors, before you talked about how the curvature
Yeah.
of the the surface, if the electrons don't see each other, they don't act on each other.
Oh, right.
So that's why designing a capacitor, with the kind of like the foil,
Yeah.
is more efficient than two plates.
Yes. And you'll also notice I have not actually done a numerical calculation for a capacitor that is much more complicated in shape. We will save that for your upper division calculations. And so it's been a while since I said it, but in Physics 121 I said it a lot. The goal of this class is to take your basic physics from 102 and your wonderful math you've learned up to Math 160 and put them together. Next year when you transfer, you're going to go into your E&M class and your teacher's going to say, okay, now remember your basic physics that you first learned in 102 and then expanded on in physics either 121 or 122, and then take your wonderful math you learned about complex surfaces in Math 200, and let's do our calculations and come up with something, and we'll do capacitors that are more complicated in shape. So we won't be doing more complicated shape calculations, but eventually you will, and your education will grow as your physics and your math knowledge grow. Yeah. Well, these charges are not any closer. Now, if you want to start saying, well, what you really have is you have these charges that are close and these charges, and if you want to think of this as a capacitor and this is a second capacitor and they're hooked two capacitors together, you can get away with that. And we will do things like that. But for this case, I don't think it makes a whole lot of sense. Remember, this charge here is not the same as that charge, and every capacitor should have the same charge on each plate. Okay, and so looking at this as a capacitor here and a capacitor here hooked together, I don't think makes it any easier. Just, and in fact, it actually makes it harder. And I'm not sure calling this a complete capacitor would be valid. If, as you pointed out, this was a metal piece, then the charge on here and the charge on here would be the same. And then thinking of it as one capacitor, then a second capacitor, and asking what's the equivalent of those two capacitors would make a lot of sense. And you will be asked to do that. Exactly. Which, I'll bring it up now. I almost said that when you asked your question, going, okay, we should do that. But anyways, this is a chance to bring up the dielectric constant. Now, the good thing, as we just said, is we get more strength, if you will. In fact, you can begin to see it in this equation. This capacitance, which I will call nu, and if I compare it then to what I'll call the old one, or the one that was just filled up with air, you can hopefully see that the new capacitance needs to be calculated with epsilon naught over d times kappa. The old one was just epsilon naught over d. So this dielectric constant is easily measured, and that's what you were asked to do in the lab. That's what step 8 was all about. Find the dielectric constant of your material. You were asked to measure, just like I did, what is the capacitance before you put the vinyl in there. Then measure the capacitance after you put the vinyl in there. And in our case, if we actually do a number here, we have 497 divided by 145. And I'm not sure what that comes out to be, but I will calculate it here. 497 divided by 145, and I get about a 3.4. So 3.4 would be the value of the dielectric constant of this material. And the capacitance has increased by that much. The electric field has decreased by that much.
Should we be thinking about the dielectric constant connecting it to permittivity, or should we
No, so now, I guess what we can call this then is, here's what you are saying. This, which is sometimes just labeled as the permittivity of the material, right? So the permittivity of the material has changed, right? Okay. And it has increased from the value in free space by this factor of kappa. And that's a good way to think about it. And you should start thinking about it. Truth be told, though, we won't do too much materials in this. We do a little bit now. We do a little bit near magnetism. But doing most of the E&M with materials in it is kind of the next step. So we're going to spend most of the semester, hey, let's just get started with free space. And you feel, once we get done with this semester, the next semester, wherever you transfer to, you will then start adding to that. In your next class, you'll say, well, okay, let's put our material in there. So this is kind of setting that stage there. But it's a good, like I said, needs to be introduced now, so you'll be ready for it in the next semester. If you open up your book, you will see that your book lists a whole bunch of material and says, what is the dielectric material of all these? And so it starts off and says, hey, let's take a look at dry air. Let's take a look at quark. Let's look at mylar. Mylar looks like it's about a 7. Rubber looks like, no, I'm sorry. Where's mylar? Mylar is about a 3.2. Rubber goes up to about a 6.7. I was hoping to see vinyl in here. I don't see it. But it looks like my vinyl is very close to that rubber there. And not a surprise that it's kind of close to this area. Huh? Yeah, and it's kappa, by the way, not K. But yes, so it will be different based on the molecular structure of it. So obviously, if you want a lot of capacitance, you would like to have this dielectric constant high. But with that said, there's a negative part of this. And here's the negative part. What happens if we start to charge this capacitor more and more and more? Yeah, remember this molecule that's being pulled? Isn't there a certain limit? This molecule can only be stretched so far. If you put too much charge on this capacitor, what's going to happen? Yeah, I may be drawing a picture back here. Remember, inside here, we had a molecule that, as it was being stretched, the negative stuff on the molecule was going one way. The positive, the atoms, the nuclei themselves are getting pulled the other way. If you get too far, what's going to happen? You'll rip it apart, right. It'll stop being, say, a solid. It'll turn into a gas. These things will fly apart. You will have charges going through here, moving back and forth. Because remember, we said, there is no such thing as a perfect insulator. You guys talking about in terms of the air. Can electrons flow through the air? Yeah. There's nothing as a perfect insulator. There is a limit to how much you can build up that charge. And then they will start to tear apart. So, those of you who might have been looking at this chart, you will see that next to the dielectric constant, they put another word. They put the dielectric strength. And what they're trying to say there is, you can only get this field so strong, and then it will tear those molecules apart. And unfortunately, once you start putting molecules in there, you have now opened the door of tearing them apart. So in that sense, the dielectric is a bad thing, because now I am limited to how much voltage I can build this up to. And looking at this chart, it says if I fill it with air, I can get as much voltage as 3 million volts per meter. Now, I know that sounds like a lot, but 3 million volts per meter means that if I have one of these small capacitors filled with air, and that capacitor is only having a distance of 1 micron, the voltage, which is the electric field times the distance, would be 3 times 10 to the 6th times 1 micron, and you're talking about don't exceed 3 volts. You exceed 3 volts, you exceed 3 million volts per meter, and the air inside will be ripped apart. Yeah.
So if it was ripped apart, would it be considered a plasma or a gas?
Plasma. Yeah. I guess I'll call it a plasma. It's a lot of everything. As they move, they hit other things and they go shooting out, so then you have just particles, just chunks of pieces going everywhere. And so it's just a big explosion, if you will, inside here. Now, fortunately, they're not very big. But that's why, as you guys noticed in the lab, and you might have even heard me talk about it last time, I have a very large capacitor, 1 farad. How did we get such a large capacitance? Small distance. What's the consequence of a small distance?
Less electric field.
Yeah, very less potential. The electric field's still going to be the same, but I can't charge these up very much. And this one says do not exceed 5.5 volts. If you exceed 5.5 volts on this, you will tear the material apart inside of it. Now, other ones, like this one here, do not have nearly as much capacitance because they purposely designed them to be a little bit further apart. And this one says it has a capacitance of only 10 microfarads. But now what's the advantage of the plates being further apart? Right. I still can't exceed my 3 million volts per meter, but my distance is more, and so this one says do not exceed 50 volts. And that is far more workable. This big one that I was working with, and the reason I used that one and not one of these, is this one says do not exceed 600 volts. And so everything's going to have an upper limit.
The 3 million volts per meter, though, that's for air.
Fair enough. These is in air.
So
Yeah.
what's in there?
I don't know. But if I did, I could go through the same calculation, paper or nylon. Okay? And the reason I say I don't know is this one's kind of fun to do. Because this one is actually made out of a, what it is, I don't know. But I know it's a complex organic molecule. The reason I like that is when it tears apart, it turns into a bunch of gases, like water vapor, carbon dioxide. If I have a container filled with gas, what happens?
Oh.
The pressure builds up. If the pressure builds up enough, what happens next? It opens up, right? Let's give it a shot. Yeah.
When these these things with displacing things like a plasmonic hotspot, is that what it is?
A what?
Is it, how do they? What exactly is it? What
Yeah, you might just want to call it burns.
Okay.
It burns. You ruin the material.
Do you know what the process is called, or specifically, or?
No, just we burned it up.
Okay.
And throw it away. It's not going to work again. and that's what I'll do here. Now this one I'll crank as high as it will go, which, although it says 50, and I'm not going to mess with the 50. Here's why, and here's why I know it's an organic material. Some of your dielectrics, if the molecule's real complex, the electric field one way can handle a lot more than the other way. So this molecule can handle a lot one direction and very little the other way. So if I do 20 in reverse, I'll easily burn it up, even though it can handle 50 in the forward direction. So not many capacitors, or maybe I should say, some capacitors have a direction. You will notice at this point I have just never even mentioned a direction. I have just always treated it as open space between them, and it wouldn't matter whether I hook positive negative or positive negative. This one happens to matter. More on that later, but we don't, like I said, do much with our capacitors that have materials in them. Because as I jokingly talked about in lab, but also very seriously, we try to make all of our lab equipment idiot-proof. And if we used one of these, somebody's going to burn it up. There's no doubt about it. And so we just hook it either way, you're fine. But not all capacitors work that way. So what I'm going to do is start with it off. And it says to put the negative on this side. So I'm going to put the negative on that side. Just because I can, I guess, right? And then I'm going to put the positive on this side. And tilt it up so maybe you guys can see it. And no, don't worry, it's not going to blow up the whole room or anything. Just go, right, okay. And so I'm going to turn up all my dials here. And watch it. It takes 5, 6, 7 seconds before it gets hot enough and enough pressure builds up, but it will. Oh, hey, that was a pretty good one. That was one of the better ones. Good. And you'll see it explode. And as long as it's exploded, let me pass it around, and you can look at it. And no, I tell you, it's done exploding. But what you'll see is the two metal plates kind of used to be wrapped up in a coil, and now they're kind of stretched out there. And it's cool enough to touch now. And so there is, like I said, an illustration of you got to be careful on your dielectric strength there. All right. Well, one more thing here, and we're done with the chapter, which is actually makes the timing good, because then I can do a bunch of examples for you on Tuesday, and you can take the test on Thursday, and blah, 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 blah. Okay, so what happens now if we start to hook these up in a circuit? What if we hook up more than one capacitor? All right, so let's start here. Let's start with a quick discussion about what if I were to just take a capacitor. Our symbol for a capacitor will be this, just two parallel plates with wires coming out. All right, so there's my capacitor. Then, if I were to hook that to a power supply, and a power supply that is not too much voltage, that we exceed the dielectric strength of the material, and I connect it, what will happen? And maybe I should just say, let's say this is 5 volts, because I actually really want to hook it up here in a minute and say, let's take this guy and set it at 5 volts. And really no different than we did before. We had a capacitor. And I'll take the big capacitor. That way things will happen slow enough that we can actually see what happens here. But it would be true for any capacitor. As soon as I hook it up, and let me pause, I put 5 volts, but I put a new symbol on the board. Now, at least in this class we haven't used yet. And so the symbol for a battery, a symbol for our power supply, we're going to use this. It kind of looks like the capacitor, but what's different about it? Yeah, one side's bigger than the other. And the bigger side is representing which one has a higher voltage. Okay? And so when we make our batteries, as I don't have you here today, but I showed you, we take some chemicals. The one in your car, it would be sulfuric acid and lead. A battery that you might have in your calculator could be the zinc and carbon old standard, although you probably buy the more alkali ones so they last longer. But there's some kind of chemical in there that is producing the voltage. And so what that means then is the chemical reaction has created a voltage that is higher here than compared to there. So remember then, electrons then want to come out the back, right? Maybe it's worth repeating chapter 25. I have a pen, I drop it. Why does it fall? It wants to go to lower energy, right? So, what's going to happen to an electron? Where does it want to go? Lower energy. Does that mean lower potential? No. It means higher potential, right? That's what we're putting there on the board. Remember, the change in energy is equal to the charge times the change in potential. So an electron, which is negative, is going to head towards higher potential because that represents lower potential energy for the electron. So this electron kind of heads in this direction. Now here's what's kind of interesting. What will happen to this electron as it gets onto this plate? Can it go over to that plate? Nope. So I'm going to put a little minus there to say, well, there's what happens. It goes up to that plate and kind of runs out of conducting room. But the process doesn't stop. What happens now? Right. It creates an electric field. The electric field is between the two plates. That electric field then does what on the other plate? It pushes an electron away, and the chemical reaction, the redox reaction that's happening in the battery, completes. And so one electron goes out, one electron comes in. It's just not the same one. And then what happens? It doesn't do it again. Sends out a second one. The second one chases off another electron. It goes around. Does this keep going on forever? No. Because as we are putting electrons on here, isn't this creating an electric field? And what does this electric field do to these electrons that are trying to get on there?
Pushes back.
It pushes back. So the first couple go on real easy. The next ones are going to have a little more trouble. Maybe they'll still make it. But eventually, what's going to happen? Eventually, they will stop piling on there. And that is what I was saying and showing for you, saying I have now a completely charged capacitor. Now what I mean by that is I have it completely charged for that 5 volts. What if I turned up the knob to 7 volts? Well, then it would put more on there, right? So looking at that capacitor, what's the voltage on the capacitor when it stops building up more charge? It does go up to 5 volts. How do you know that? Right, what we mean by that 5 volts is that's the amount of push. We are saying this battery is pushing with 5 and it will overpower the capacitor until the capacitor pushes back with 5. In other words, they seek the same force or the same energy. If this helps, I like to think about this picture. Think of this battery as a giant source of electrons, water. And so these electrons are represented here with water. I have a huge tank. And the reason I say the tank is huge is because this tank has a depth of 5 meters. And if you let some water out of the tank, it really doesn't change its depth. It still is 5 meters. And that's kind of how a battery works. A battery keeps having 5 volts until the chemicals run out, and then, okay, then it starts to drop away. But as long as we have those chemicals and they keep reacting, we always have about the same height. What if you were then to hook this big tank to an empty small tank? What would happen? The water would keep flowing in. If forever? No, when does the water stop flowing? Yeah, when it gets to 5 meters. When the forces balance. When the energy levels are the same. And so this capacitor is going to start building up quickly at first. Then not so quickly. But after a long period of time, and for these capacitors, this long period of time could be a couple of nanoseconds, it'll be full. Now this one will take more than a couple of nanoseconds. And so let's take a look at it. This time, unlike we did last time, yeah, well, I'm going to use this one at 5. So good point. But so you can actually have a visual effect, I'll start with it off, I guess. Feed the electrons through a light bulb so that while the capacitor is being charged, I will have some kind of visual effect as they flow onto there. So you might say in this picture here, I have installed a little measuring device called a light bulb that as the electrons are moving, I should be able to visually see them. And I claim that you will see it really bright at first because they're going to flow on there right away. And then it'll get weaker and weaker and weaker. So I turn it on, it's nice and bright. Now the capacitance is developing a voltage, it's pushing back, maybe say 2.5 volts. And so the net effect is, 2.5. Then this gets to 3, so the net here is only 2. Then this gets to 4, so the net effect is just 1. And of course it's getting dimmer and dimmer and dimmer. And eventually the capacitor will be completely charged and nothing will be flowing anymore.
So it'll fully break throughout the capacitor once it's fully charged?
Sure. Okay. But that is kind of this first scenario. So if I were to ask you, how much charge is on this capacitor, could you answer that?
Yeah, it's not flowing anymore.
Okay, so once this capacitor gets completely charged, could you tell me how much charge is there? Yeah, what is it?
Q equals C.
All right, so Q divided by V is my capacitance. This capacitor is 1 farad. The voltage it is now at is 5. Now notice I said after it is completely charged, because it wasn't 5 until a long period of time. But right now, it is at 5. And so I can answer probably the easiest of these questions, and that is, what is the charge when I have just one little capacitor or big capacitor and one battery? 5, remember a farad, excuse me, is a coulomb per volt. So volts would cancel, and I'd be left with coulombs. So the charge is 5 coulombs. So I should have 5 coulombs of charge on all those plates that are in there. But let's add to this. What if we change it? What if we have 2? Call it C1 and C2. Now, in the interest of time, maybe I'll go a little quicker, not actually hook it up here. But what would happen?
They both fill up.
They begin to fill in both, right? I mean, that first electron would come out here. It would flow around. It would get to right here, which we're going to call a node. And it would say, look, I can go this way, I can go that way. It really has no preference. It probably goes the shorter distance first and says, okay, there I am. But what about the second electron? Yeah, it probably goes over to there. What about the third electron?
Either way.
Now, same type of question, but now 2 capacitors here. And maybe to be complete, every time one electron went on the bottom plate, it chased another one off the top of the plate, so they go around. But it's a little more complicated. Do they keep flowing forever?
No.
No. Maybe if it helps, let's come over here to this bucket of water again. Because what I'm really asking is, what if, in addition to one bucket, I had a second bucket? Do both of these buckets keep cleaning up, keep building up forever and ever and ever? No. When do they stop? When they're both at 5 volts. When they're both pushing back. Do they have the same charge? Yeah, let's look at this bucket here, right? This bucket will fill up to 5 meters. This bucket will fill up to 5 meters. Will you have the same amount of water in each bucket? No. So I'm not trying to say that they fill up until they have equal amounts of charge. It's not like 1, 1, 1, 1, 1, 1, an equal amount of charges. And that's kind of how I indicated as I was starting. That's not what stops them. What stops them from going on to the plate back here was the strength of the electric field. And so if I draw the electric field in here, electrons will keep piling on in such a manner that not necessarily are their charges on the plates the same, but their voltages on the plates are the same. If we let this keep going, eventually this will build up to 5 volts, and this will build up to 5 volts. They will have the same voltage. And then the 5 volts that is pushing out to here can't go any more this way because it's blocking it, and can't go any more that way, and it's done. If more electrons went here, and I don't mean necessarily more in number, but I mean more so that the voltage is bigger. If this builds up to 1 volt, it's not as if it's going to keep going until 5 and then start filling this one up. If this one is already pushing back to 1 volt and this one is not, then they will go this way. And so what will happen is the voltage on these will always be the same. Isn't that what happened in this bucket? If you start pouring water into here, and maybe I shouldn't have had the hose touching the top of the tank. I should have had it touching the bottom of the tank so it can easily flow in. But it's not as if this one's going to fill all the way up and then this one starts to fill up, right? it'll always fill it up with the same energy, the same push. And so as this thing is filling up, the water levels, the voltage levels will be the same. And they will stop filling up when they get to 5 meters. They don't stop when they have equal amounts of water in them. They never had equal amounts of water in them. They had equal voltage. And so this is what I'm getting at. We are going to call this a parallel connection. Why? Well, we have an option, right? When the electrons come out, we can go this way or we can go this way. If you were in your car driving to Carp, you would get on the freeway and you would have 3 parallel lanes. You would go in the first, the second, or the third lane. You would only need to go down 1 lane to get to Carp. You don't go all 3 lanes and back and forth and back again to get to Carp. You don't have to go from one into the other. And that's what these electrons are doing. Some electrons go here and some electrons go there. When 100 people drive to Carp, some of them go in 1 lane and some of them go in another. And they get to their place, right? And in this case, they're going to slightly different places once they get to here. But in this area, we have a parallel. We have an option. And so hence we're going to call this a parallel. Now, if I were to ask you, how much charge is on each plate, this probably wouldn't be too hard to calculate how much is on each plate. Fair enough? How would I get the amount on plate number 1? Right. It would be the capacitance times the voltage. And so we're talking about the capacitance of number 1. How would I get the amount of charge on plate number 2? Yeah, capacitance number 2 times the voltage. Now notice I just put voltage because you already told me that something like this, something that's in parallel, should always have the same voltage. Again, it's back to forces. If they did not have the same voltage, if one tank had a higher level than the other, they would push around and go to the lower potential. And so they will keep the same all the way up. And so this is our parallel. I'll even do one step more. I claim that this, or these, I guess I should say, 2 capacitors are really the equivalent of 1. Right? I mean, physically they may go on different plates, but the process is really identical to something like this, where the charge comes out of the battery. In fact, let's take a look at this. You already told me that the voltage on each capacitor would come out to be the same. What about the charge? Is the charge on each of them the same? No, not necessarily, right? What do you notice? The charge is what? Right. They could have different capacitance. Could you tell me how much charge came out of the battery?
Yeah.
How much came out of the battery? How much charge came out?
Just some of the charges.
Exactly, right. So what came out of this battery would be Q1 plus Q2. Right? And why would you even say that? Conservation of charge, right? We're not creating any of it. So what comes out of the battery, even though it's split right here, the stuff that goes this way, added to the stuff that goes this way, it's got to equal the stuff coming in, right? Those of you in your circuits class, you've already been doing that. What do you call that? KCL? Kirchhoff's current law, right? It comes from your conservation of charge, right? And that's what you'd want to see. Now, here's what I want to do then. Just because it is so easy to calculate something that has 1 battery and 1 capacitor, is there any way I can view this as the equivalent? Yeah. I claim that even though it's actually this, I can think of it as one capacitor for reasons of maybe making my calculations easier. And so my question is, what would be the equivalent of these two capacitors? Right. And maybe you see it. You already told me that they would have the same voltage, and the charge that comes out of the battery is Q1 plus Q2. So when I look at this scenario, I will go Q total comes out of the battery and goes on that capacitor, right? In other words, the equivalent capacitance would be the charge total that comes out of the battery going on our 5 volts. But if I take this conservation of charge that you said here and apply it to this step, I would have charge 1, charge 2 divided by V. If I separate that into two pieces, what's this first one? Yeah, there's C1. What's this? There's C2. And so two capacitors that are hooked this way, what we call parallel. You can take those two, merge them together, and it's pretty easy, just add them together, and now you can do a simple calculation to find out what the charge is and what the voltage is. You also need to remember that this equivalent circuit is not the real circuit, so we might have to come back to find out how much individually is on each one. But if your goal was to find out how much charge or how much current, this would be nice to take two capacitors, put them together and say, I don't really have two capacitors. And that's the little trick I want you to see. And 2/3 of you already did this in the lab. I wish I had gotten this far before you did the lab, but you are taking in lab two capacitors, you hook them in parallel, and you measure them. Then you measure them individually, you add them together, and see if you don't get the same thing. And you should have, because I told you don't go any further in the lab until you get it. All right? Let's try a different hookup. Let's change this a little bit. Let's come, and I guess I'll keep this pattern over here, but let me change my picture a little bit. Actually, a lot. Give myself a little more room to my battery. What if instead I hook the capacitors this way, which is trying to say this metal plate from number 1 is connected to a metal plate on number 2. What would happen here? Well, wouldn't the electron still come out? And where would it go? Would it go to number 2 or number 1? Can it get to number 1? No. So that one electron can do nothing more than go on the plate for number 2 by the way it's hooked there. Now that's not the end of the story, because what will happen next? Yeah, it's going to create an electric field which is going to push an electron off of this plate. And where does it go? Has no other place to go. It goes to C1. And then what happens? Yeah, it creates an electric field in C1, pushes off an electron on the other plate, and finishes our redox reaction. And now a second one does it. And when a second one does it, it chases one off, puts one here, and chases another one off there. The third one chases one off of there, puts it there, chases one off the second one. And I'll just do one more here for the picture, but hopefully you notice something. Does this keep going on forever and ever and ever? No. It eventually stops. When does it stop? Right. When the voltage added together is 5, not 5 on each. See, what's happening, if you draw a picture of the electric field, is this is pushing the electrons back, and so is that. That's part of the whole path. So these guys are pushing back, and until those add up to 5. So V1 plus V2 has to equal V. Charges will keep flowing on there. So, do either of these charge up to 5 volts? No. Total that charges up to 5 volts. So, this is a slightly different connection. And the slightly different connection gives us slightly different results. And so, the physics is still there, that we're going to do our pushing, our pulling, our conservation of energy, and our conservation of charge. But we end up with a different result. So we call something that hooked this way series. And again, hopefully the name makes sense. Doesn't it show that what happens is it's got to go to the first element and then the second element, right? And so we call this series. If you were driving from here to San Diego, series would be drive on the 101 until you get to the 5. Then take the 5 until you get into San Diego, right? And so that's our connection, our series. What about the charges on these guys? How does the charge on, say, number 1 compare to, say, number 2, compared to, say, what I'll call the total coming out of the battery? What do you notice here?
It should be equal to the capacitor. The Q1 and Q2.
Are they equal? Are they equal all the time or only some of the time?
Well, it depends on the capacitance.
No, it does not depend on capacitance. Isn't the charge always going to be the same? Where did these negatives come from? From that one. Any charge on number 1 came from number 2. So how much on charge 1 compared to charge 2? It's got to be the same. And so things that are in series like this are going to have the same charges going through them. You guys in your circuits, you've been doing that with resistors already, right? You got one resistor, you got another. If you got a certain number of amps in one, doesn't it have to be the same? There's no place else for those charges to go. That's a conservation of charge statement. It's got to be the same. And in fact, where did the charge on number 2 even come from? From the battery. So how does this compare to the charge on the battery? It's got to be equal. Conservation of charge. Right? And so again, conservation of charge, we're going to just keep calling it, and eventually call it Kirchhoff's current loop law. Right? We're just going to say, look, they got to add up. This was discovered by Kirchhoff, and you're going to see that real soon. So you guys in circuits have already been using Kirchhoff's name, so I might as well throw it out there now. This is a conservation of charge statement. This was his argument. This is why it works. You've also noticed the other thing. What are you noticing about the voltage here? Why did you say the voltage of these two added together have to be 5? Because you're saying you get a balance, right? If you went on a little hike in the mountains, if you parked your car right here at the trailhead, and you realize this trail is a loop, some people will go around the loop clockwise. Some will go around counterclockwise. I don't care which way you go around this loop. You may go uphill and then downhill. Or this way, uphill and then downhill. How do your uphills compare to your downhills? They've got to be the same if you're going to end up back where you started. So what do we see here about the sum of all the energy? The sum of all the voltages around a loop. They gotta add up to 0. This is a conservation of energy statement. And we will talk about that in future chapters and call this the Kirchhoff voltage law. Kirchhoff's voltage, I'll just keep calling it conservation of energy. All right? And so this is conservation of energy. It's also conservation of charge. If you put those two principles together, you can solve all of these circuits. And that's really all you need to know for circuits, is conservation of energy and conservation of charge. And then, of course, kind of get the mental picture of what's going on here. Now, keep that in mind, because here's my question for you. Like we did over here for the capacitor that was in parallel, it might make it nice to think of these two as just one capacitor. And so, even though it's physically 2, I'm going to draw a picture like this and say, what's the equivalent? Well, this is kind of the key. Voltage is V1 plus V2. So notice the voltage on each of these capacitors is less than the 5, less than the total. It's not necessarily 50-50, because how would you calculate the voltage on capacitor number 1 using the charge and its capacitance? Yeah, this would be the charge on number 1 divided by its capacitance. How would you get the voltage on number 2? Charge on number 2 divided by its capacitance, right? Now this side, this is the total voltage. So if I look at this equivalent circuit, now again, I'm not saying this is really the circuit, because this is the real circuit. But what I'm saying is I can kind of group those together to make my life a little bit easier and say this would be the equivalent, and if I write this, it would be total charge over this equivalent capacitance, right? And so this line becomes this line. But now remember what you told me back here, because of conservation of charge, isn't the charge on every capacitor the same and in what came out of the battery? So can't these be canceled off? And so the equivalent capacitance can be calculated with what's called a harmonic sum. The reciprocals add together and gives you the reciprocal. So there's a few more steps in order to get the equivalency. But this is for series. And the other one is for parallel. So half your battle when you start working on these problems is to kind of stop and say, are these capacitors hooked in series or are they in parallel? We'll see if this helps. When do you know when they're in series? Yeah, if there's a line connecting one to another, they got to go from one to another, right? No place else to go. If they're in parallel, that means there's a choice, but that means the opposite side. You could go one direction or the other. So you can loop this way or you can loop that way and get it. One last warning, especially for those of you in the circuits class, notice the pattern of these equations is opposite to the pattern that some of you have already seen for resistors. So we're going to be doing resistors also real soon, and I'll give everybody that warning, but the patterns are reversed, and so it's easy to forget what you're working with. But in our case, so far we're working with capacitors, and that's the equation.